Here is section 3.6, and in this section our big essential question is how can you solve a quadratic inequality? So let's look at our learning targets. First, we're going to graph quadratic inequalities in two variables. We're just going to be graphing our quadratics, and we've been graphing several of these. Now we're just looking at the inequality, right? So I don't have an equal sign anymore. I have a less than, I have a less than or equal to, I have greater than, and I have greater than and equal to. These are going to be the four symbols we're really looking for. Then we're also going to be using graphs and algebra to solve our quadratic inequalities. So let's take a look here. So first, we want to graph our inequality just like we've been graphing quadratics, right? So we want to get this in standard form, my ax squared plus bx plus c. We graph it. We can use Desmos, but we do also want to know how to graph it by hand, right? So by finding the vertex, figuring out the direction it opens and closes. The only difference is now we no longer have this equal sign. We have a less than or greater than, and when I have those, I have a dashed line, right? So it's going to look something like this because my answer is not included. When I have a solid, so when I have an equal to part in there, it's going to be a solid line. Okay, so first I kind of graph it and I determine, is this going to be a dashed line or a solid line? Then I test a point inside the parabola, and really you can test a point anywhere to determine which side I shade, because we're going to be shading here, and we'll look at a couple of these examples. And then I shade where my solutions are true. So first I want to graph this. Y is less than negative x squared minus 2x minus 1. So the first thing I do is I find my vertex, or I can go ahead and use Desmos to graph it. And here is this equation graphed. So I have a negative x squared minus 2x minus 1. So what I really know is that this is not actually going to be a solid line. This needs to be a dashed line. And I know that this needs to be a dashed line because I do not have an equal part. It's just less than. Okay, so it's telling me it's less than. So now I have to determine which part do I shade. Do I shade inside my parabola or do I shade this entire outside parabola part? So what I really like to do is I like to use the point 0, 0. And I like to use that point because it actually makes life a little bit easier. Okay, so let's test the point 0, 0. So what I can do is I can plug in 0 for each of my pieces, right? And I always want to use parentheses when I'm substituting. So I have 0 is less than, 0 squared is still 0, and negative 0 is 0, minus 2 times 0 is 0, minus 1. So 0 less than negative 1. This is not a true statement. So I know that I do not shade where 0, 0 was. So in this parabola, my 0, 0 is outside, so I would be shading inside my parabola. And so if I go up here and I actually just fix my equation, there you go. So this is exactly y is less than my negative x squared minus 2x minus 1. And you'll see now that I have my dashed line because it's not part of the solution, and I'm shaded inside my equation. So that's what it would look like when I graph that. Okay, so now here's kind of a word problem we're dealing with. So a manila rope used for rappelling down a cliff can safely support a weight in pounds, provided that that weight is less than or equal to 1480 times the diameter squared. And I know that d is the diameter in inches of the rope. So I want to graph it and interpret the solution. Okay, so here you'll see my graph. And here I also want to note that my graph starts at 0, 0. Okay, and I know that I can do that because I cannot have a negative weight and I cannot have a negative diameter. So I have to keep that in mind when I'm drawing my labels for my graphs and when I'm including that information in my graphs. So I go ahead and I graph this 1480d squared. One thing I note is it's going to be a solid line, right? This tells me it's going to be a solid line because of this equal to part. So I graph it and then I test a point. So first I graph my w equals 1480d squared. I test a point. We're going to go ahead and pick this point. It doesn't matter which point you pick, but we can pick that 1, 3000. So let's test it. So I know that my w is 3000, less than or equal to 1480 times my d, which I picked was 1, squared. So this d I can go ahead and replace with the 1 of the point that I picked. Okay, so generally when you're picking points for your parabola, you want to pick points that are fairly easy to use. So here, an x value or a d value of 1 makes life pretty easy. That's also why I like to pick the origin often. Okay, so when I simplify this, I end up with 3,000 is less than or equal to 1480. This is not a true statement, right? Because 3,000 is greater than that. So I know I shade on the part that does not include this point. So since this point that I picked was inside the parabola, I'm going to shade outside of this point. Okay, so that's really another way I can graph these things. So when I'm interpreting these solutions, the shaded area tells me all of the solutions, right? So my diameter, if my diameter is 1, it could support a weight of any of this part down here that's shaded. Well, if my diameter is 2, it could support any of these weights here. So the shading just tells me where it can support according to this problem. Okay. So now we're also looking at some systems of inequalities. So here I see I have 2 different quadratics, and they're both inequalities. So the first step I want to do is I actually have them both here. So here are both of those equations, right? So the orange one is that top one, negative x squared plus 3. The purple one is that x squared plus 2x minus 3. So first thing I graph both pieces, and then I have to determine, is this going to be a dotted line or a solid line? So here, this top one, this is going to be a dotted line because I do not have the equal to part. This I'm going to have a solid line. So now I have to determine where I want to shade each one, and we can look at them individually. And again, I'm going to pick the origin for both of these because according to my graph, the origin is inside both parabolas. So let's use the origin. As long as the origin's not on one of the lines, I can use it as my testing point. So let's try it in this first one. So 0 is less than negative 0 squared plus 3. So I have 0 is less than 3. That is true. So that I know I can shade. If I go back to my graph, this orange one, I know that I picked the origin, so I would shade where the origin is. So it would be all in here. That would be shaded. And we'll look at that in just a second. So now let's try the origin for the second equation as well. So 0 is greater than or equal to 0 squared plus 2 times 0 minus 3. Well, this is 0 and this is 0, so 0 greater than or equal to negative 3. That is also true. So looking at the purple graph, the origin is also inside the parabola, so I would also shade inside the parabola. Okay, so let me go ahead and fix what we were looking at. Okay, so again, here is the actual graph. Again, the orange one has that dotted line, and it's shaded inside. The purple one is a solid line, and it's shaded outside. So when I'm looking at these systems of inequalities, I know that the solution that I'm really looking at is where the shading overlaps. So we can see that in this little part in here, that's kind of the really dark purple, this is where all of my solutions are. So I could pick any point that falls in this area that's double shaded, and it would work for both of my equations. So that's what we're looking at for systems, is what works for both. And anywhere that's in this shaded area that's shaded by both of them will work for both of my equations. So here are some to try. Definitely be able to kind of get the picture of the graph in your mind before you use Desmos. And also double check, is this going to be a solid line? Is this going to be a dotted line? Do I shade inside the parabola or do I shade outside? And how do I know? Okay, so now we're going to be solving this algebraically. Okay, so using algebra. So let's go ahead and substitute, get rid of this sign, and just substitute. So now I have x squared minus 3x minus 4 equals 0. Okay, because I've solved some that look like this before. Well, I see that my a value is 1, and I have a fairly simple c value, so I'm going to go ahead and factor this one. So I first want to find all of my factors of a negative 4. So I know I could have 1 times a negative 4, or I could have a negative 1 times a positive 4, or I could have a negative 2 times a positive 2. So now let's add these together. So I've got negative 3, I've got positive 3, and then I've got 0. Well, my middle term, my b term, was a negative 3, so this is what I'm going to be using. So now I have x plus 1 times x minus 4 equals 0. And then I use my zero product property. So x equals negative 1 or x equals 4. So now I have these two solutions. So now I have to actually continue to solve it. And to do that, I go ahead and I draw my number line. Okay. So here is my, let's see, we're going to start with negative 1. So there's 0, 1, 2, 3, 4, 5. Okay, so first thing I know is that I'm going to have an open dot on both my -1 and my 4. Let me go ahead and use a different color for this graph. So I have an open dot on my -1 and an open dot on my 4. And these are my two values here. And I know that it's an open dot because back in my original equation, I did not have an equal to. I did not have that line underneath. If I had the line underneath, it would be a solid dot. So now that I have this kind of picked out, I have to test 3 different points. So I test a point that's down here, I test a point that's here in the middle, and I test a point here on the end. Okay, so let's go ahead and test a -2. Let me just scroll down a little bit. So I'm just going to rewrite our equation, x squared minus 3x minus 4. And we're looking for that to be less than 0. So let's test -2 for this first chunk. And I'm picking these points that are in between. I need one that's less than this dot. I need one in between, and I need one in over here. So we're going to pick -2. So I've got -2 squared minus 3 times -2 minus 4. You always want to use parentheses when you're substituting. So -2 squared is 4 minus 3 times a -2 is a -6 minus 4, less than 0. So I end up with 4 minus a negative is plus 6, which gives me 10 minus 4, which is 6, is less than 0. That does not work. So I know I do not shade over here. So now let's pick a point in the middle. And again, I see that 0 is in the middle, so we're going to use 0. So I have 0 squared minus 3 times 0 minus 4, less than 0. Well, that cancels out. So I have -4 is less than 0. That one works. So I know in my graph that I would shade in between these 2 points because that one did work. So this is definitely shaded. But I always have to try this third anyways. So let's go ahead and use 5 since it's right there. So I have 5 squared minus 3 times 5 minus 4 less than 0. So I've got 25 minus 15 minus 4. 25 minus 15 is 10 minus 4 is still 6. So I have 6 less than 0. That does not work, so I know I don't shade. So my final solution here, let's do this in purple. My final solution is -1 is less than x, which is less than 4, because x fell, this worked in between here. Okay, so when I'm looking at solving these algebraically, I have to find my 2 solutions by either factoring, quadratic formula, whatever. Find your 2 solutions, and then you need to actually test in between each piece to find your final answer, which in here it ended up being the middle piece. So my final answer was this -1 is less than x, which is less than 4. Okay, so now we want to look at this last one, and we kind of want to solve this by graphing. So when we are solving this by graphing, there we go. We look at this one here. So here is kind of what that looks like. And when we solve, remember, we find the x-intercepts. And on Desmos, it's pretty cool that you can just click them and it knows that's what you're looking for. So here I see that those are my solutions. But now I also need to know this is an inequality. So is this going to be in between, or is it going to be everything that's outside? Okay, so first I know that this has to be a solid line because I have this equal to part, and then it's going to be greater than. So I can pick 0, 0, our good old friend 0, 0 to test that point because it's in here. So let's try that. So 3 times 0 squared minus 0 minus 5 greater than or equal to 0. So 0 minus 0 minus 5 greater than or equal to 0. -5 is not. So I know that I will not graph where the origin. So that means that I'm going to be graphing everything outside of where the origin is. Since the origin's inside the parabola, I go ahead and graph what's outside the parabola. So let me just go ahead and, uh-oh, now it's mad. Hold on. There we go. So you'll see when I graph that, I do have my solid line because I had the equal to, and I do see that I'm shaded outside here. So the way I can end up writing this is that x is going to be less than or equal to, right? It's that equal to because it was a solid line wherever this point was, and -1.135, -1.135, or x is greater than or equal to, because it goes to this side as well, it's greater than that 1.468. So here would be kind of my two solutions. So on this last one, we had it written in between, right? I could write it, my whole solution is this, but that's because it was in between. On this example, my shading went towards the outside, so I would have an or statement here. So those would be my two solutions. Okay, so now here's kind of our word problem. So I have a rectangular parking lot, must have a perimeter of 450 feet and an area of at least 8,000 square feet. Describe the possible lengths of the parking lot. So first I like to draw myself a little picture, right? Rectangular parking lot, and I have a length and I have a width. I know that I must have a perimeter of 440 feet. So perimeter I know is 2w plus 2l equals 440. I can kind of simplify this a little bit and divide everything by 2, so w plus l equals 220. And then I know that I have to have an area of at least 8,000 square feet. Well, to find the area, I have length times width, but it has to be at least, so greater than or equal to 8,000. Well, now I see I have a simple system of equations, right? So I have some WL and I have some WL and I have two equations. So let's go ahead and solve for my W over here. So to do that, I subtract L from both sides. So W equals 220 minus L. So let's substitute. So I have L times 220 minus L is greater than or equal to 8,000. So I can distribute this. So I have 220L minus L squared greater than or equal to 8,000. Well, now I just have a simple quadratic that I can get everything over to one side and then either graph it. See, I see here that these are some kind of big numbers, so I wouldn't want to factor it. I would graph it. So let's go ahead and graph this one. So here's this graph, and I've zoomed out quite a bit because I need to see my intercepts. Okay, so here I have this negative, and I use x in Desmos, even though we were using L, negative x squared plus 220x minus 8,000, because I want to get everything over to one side first. So I would end up with a negative L squared, just putting things in order, plus 220L minus 8,000 is greater than or equal to 0. So now let's see what this says. So first I know that this is going to be a solid line, and that I'm going to be shading. So I can pick my point in practice. So I would pick the origin, but here we're going to actually kind of greater than or equal to 0. So I see that I'm shading in between here. And this kind of makes sense. So then I can find my intercepts. So 45.9 and then 174.03. So back here, what I'm looking at is these are all of my possible lengths of the parking lot. So the length needs to be at least, right? And because we're given a word problem, we have to use sentences often to answer it. So the parking lot needs to be at least 45.96 feet, right? Because we're dealing with feet, but no greater than, that would be my other intercept, my 174, but no greater than 174. Because when I'm shading in between, this tells me all of the possibilities that work, that fit exactly the perimeter that I needed and that would fall within the area lengths. Okay, so anything in here. So I want to tell me the least and the greatest. So I did this using my word problem as well. Okay, so here are a few more for you to try and just think about. So think about what's going to happen, especially in this word problem. What happens if I change my area? Okay. So now let's look back at our learning targets. So first we graphed those inequalities in two variables. And remember, the first thing we want to figure out, do I have a solid line or do I have a dotted line? And then I can figure out which direction do I shade. So then I solved these quadratic inequalities, and I was able to solve them both algebraically, so solving them and then testing each point, and then I also solved them graphing them. So now that you've worked through these learning targets, go ahead and work on your homework for this section.